Hi, I'm Bill Ripley. I'm representing Samtec here today. And we're going to be talking about Vita 90, which is the latest iteration of a small form factor standard that started out life as Vita 74 here several years ago. So I've become kind of known as the proponent of VNX here, and have done presentations on regular VNX over the years a few times. So today we're going to talk about several aspects of VNX and VNX Plus, and we're going to hit the high points on some of the changes from Vita 74 to the current standard Vita 90. So anyway, VNX Plus is often considered a downscale derivative of VPX. You can, it's an accurate way of portraying it, but it is a different standard than VPX is. But we made it on purpose to look and feel like VPX, so that if you've got if you have expertise and familiarity in deploying VPX solutions, making the change to VNX wouldn't be very difficult. So it's purpose-built to be rugged and conduction-cooled. There is no air-cooled variant of VNX or VNX Plus. And VNX Plus, importantly, is not intended to replace VPX, but just to expand the VPX architecture down into the small form factor marketplace. So why would you want to use VNX? Well, the whole idea of being able to is to be able to make things smaller, lighter, more efficient is just the holy grail. We're always trying to get more performance in smaller space. We're trying to standardize everything that we can within VNX that makes sense, but allow you the flexibility to be able to use existing MOSA standards to help you field and deploy VNX Plus platforms. So VPX and VNX Plus, it's really now becoming the mainstream for rugged MOSA deployments. The architectures are replacing custom designs. Traditionally, when you're building things small, like to go into a small UAV or into a pod, oftentimes you had to go in and build custom electronics to do that. So the idea is that now you'll be able to go in and use off-the-shelf electronics to be able to do a lot of these missions that you had to use custom before. And it's really good about fitting into available spaces. You can build small ATR-style boxes. You can put a compute module into a dumb display and turn it into a smart display. You can use them for CubeSats and small spacecraft. There's become quite a following here recently about building space VNX hardware and now space VNX Plus hardware. So the timeline for VNX, those of you that may remember, I used to be a lot thinner and I had darker hair, and that's when we started going and bringing VNX into the marketplace here about 2010. That's when the technical committee was founded, and that's about the time that Vita 65 was ratified. So in 2014, Vita 74 was released for trial use. And what that was is we wrote we wrote the essential parts of the standard, released it for a 3-year trial use period, and at the end of 3 years, the idea was that we would go in and roll in whatever changes we needed to make that a viable standard. The good news was that we really didn't have to change much in 2014 or 2017 after we went through the 3-year trial use period. So it was adopted and ratified by ANSI in 2017. And about that time, the VNX architecture in 2021 was selected by SOSA to be a small form factor standard to be used within the SOSA community. And that really breathed some new life into VNX. By the time we started looking at all of the changes that people were wanting to make, to be able to be everything that what everybody wanted, it was clear that we needed to go in and kind of, I won't say rethink, but we needed to go in and make some optimization to the VNX standard, and so we decided that it was different enough that we would call it a new number, so we assigned it Vita 90, and it's now called VNX Plus. Now, Vita 74, VNX, is still out there. We updated that standard here last year and republished it as an updated standard, as we have people that are still using that hardware. So if you look at this is a slide showing some of the volume comparisons between some of the form factors that are similar, just showing where VNX fits into the grand scheme of things. I had a module I intended to show, but I loaned it to somebody last night, and I think they left town with it. But essentially, the VNX module is about the size of a deck of playing cards. You can see my credit card sitting on top of a VNX module on the top photo here. That gives you an idea of what the size of this thing is. It's basically a credit card sized module with a connector attached to it. And we did that on purpose, in that there are several MOSA standards that are out there, like ComExpress Mini, and like a lot of the FPGA boards that are being built by some of the European manufacturers, et cetera. They're all built on credit card size modules. So we wanted to be able to go implement a new standard by using hardware that was already in existence. If you can go out and build a processor mezzanine, if we could go put this processor mezzanine card on our carrier board that we would build for VNX, we're miles ahead, because you could kick out a single board computer design in a matter of months, as opposed to a man-year or two if you were starting from a chip down, ground up design. So you'll see here that, just put things into perspective, if you have a 3U 1-inch pitch VPX module, that's about 3.5 times the volume of a VNX module. So what changed between VNX and Vita 90? VNX was originally based on Vita 46, although in the last upgrade we did take it and update it to be more like Vita 65. Vita 74 was a module-only standard. We really didn't intend to go in and come up with a system standard around Vita 74. We were going to leave it as a module-centric standard and see where the marketplace took us. Where Vita 90 is that it's module-centric, but we're going to be publishing system configurations and considerations in a systems application guide that'll be coming, that'll be released with the standard package. Vita 74 was optimized for ease of implementation. And that, if you went in and look at all the pin assignments for Vita 74, you'd see that they were very, it was obviously set up so that it was easy to go in and route backplanes and things along that line. Where in Vita 90, we optimized it for maximum signal integrity. And I've got a slide on that here in a little bit. Vita 74 was built at that time for PCI Express Gen 1 and Gen 2, and we found out that it happened to work at Gen 3 as well. Where Vita 90 was designed from the beginning to operate at Gen 3 speeds, and we've analyzed it, and it'll work fine at Gen 4 and really approaching Gen 5. The Vita 74 was available only in 19 millimeters and in 12.5 millimeter. That's the number of, you would consider the pitch, a 19 millimeter pitch, the spacing in a card cage, and 12.5 millimeters. Where Vita 90, we're going to allow multiples of 19 millimeter and 12.5 millimeters. So we'll have a 39 millimeter module for those that need that extra space to be able to go put in, receiver components or what have you. Vita 74 was copper only. We had no coax or optical apertures. When we needed to run an antenna out for a GPS receiver, for instance, we just brought the RF out on C-ray pins, and it worked fine. But with Vita 90, we knew that there was a need for bringing out optical MT signals as well as coaxial video and RF signals. So we've got apertures. We adopted the aperture strategy that was being used in VPX. VNX Vita 74 had a very simple system management functionality. So where we used an I2C interface and we could go through and get basic fault information, model number and serial number of the cards, things along that line. And in Vita 90, we have adopted a full Vita 46.11 system management scheme. But we also allow the legacy VNX management scheme for minor cards and things like that, and I'll explain that a little bit more here later. In Vita 74, we really didn't know how much power these things were going to be used for, so we put an arbitrary limit of 20 watts per module on for a 19 millimeter module. We found out that they worked very well at 25 or 30 watts, something like that. And based on the technology at the time, that was really all that we could put into it to be able to take out of it. So it was kind of impractical to go build a higher power module than that. Vita 90, we've expanded the thermals, to 80 watts per module or more, depending on how you cool it. We've got a customer, or we have an adopter, Collins, they've published on it, that are putting inside of a single 19 millimeter VNX module 2 ZU11 processors with all the support circuitry required to make them work, 4 Fireflies for the optical codecs, and 2 terabytes worth of flash, all in one single 19 millimeter module using some MCM versions of the ZU11 processor. So you can imagine the excitement of being able to get that much processing capability into a small space. So we're building a family of standards. Vita 74 is still considered within this family of standards for VNX Plus. Vita 90.0 is the base standard. That's where we define all the module sizes. That's where we define the essential pin maps for all the different slot profiles. Vita 90.1 is where we've defined the specific profiles and naming conventions. Since we've got some names that are different than VPX, we're kind of doing a translation there, a key for what we call it over here versus what it's called over within the VPX community. And we'll have a list of slot profiles, or a table of slot profiles. We envision we're going to try to do that in table form as opposed to document form. Vita 90.2 is where we have defined the optical and coax for both RF and video, the contacts and the apertures. So and that means the actual optical contacts, the RF and coaxial contacts, as well as the aperture blocks to hold these things. 90.3 is for the power supplies. That's the equivalent of like Vita 62, where we're putting the power conversion and energy storage modules. So that's the capacitor module to be able to do power hold up. We'll define the front end modules as they're required for 3-phase AC or 270 volts, or the single stage power supply modules and filter modules. Vita 90.4 is, we call it enhanced mounting, retention, and thermal solutions. So we've got a wedge lock configuration for those that want wedge locks or need wedge locks for their application. That'll be defined in Vita 90.4. As far as ways to hold the cards into a card cage, depending on how you build that card cage, particularly those modules that have a high spring force based on the coaxial and MT ferrule contacts. 90.5 is, and in 90.4, we're also defining some thermal solutions, like we've got a program going on right now to be able to define an oscillating heat pipe cooling methodology that would be useful for Vita 90. And Vita 90.5 is all the use cases and space use considerations for a space VNX deployment. So here we'll show a little bit for Vita 90.2 as far as apertures and contacts go. These are the The apertures that are either in build or on the roadmap right now for doing 50 ohm RF or 75 ohm video or optical MT with either 12, 24, 16, or 32 fibers per MT ferrule. And these are some of the aperture examples that we have for, like in the upper right-hand corner, a 2 MT configuration. The one below that is, and we have the apertures divided up into what we call a half aperture, a full aperture, or in the case of no aperture at all, it's a 0 aperture. So the half apertures are by far and away right now the most popular and the most practical, and we can have various combinations of 50 ohm RF and 75 ohm video. So in the upper right-hand corner, we have a 2 MT configuration. To the left of that, there's a size 20 RF contacts plus 1 MT. We've got the 4 video contacts, which are 16 gauge contacts with 1 MT. And you can see the rest of them here with up to, in the large full aperture, you can get 16 20 gauge RF contacts, 4 16 gauge RF or video contacts, and 2 MT ferrules. Some of those contacts can be either edge mount, right angle, or cabled contacts. So here's an image showing a typical backplane with the 2 MT configuration on top. The full aperture that we just described is the second row. The half aperture with 6 coaxial and 1 MT is shown in the third row. Then the 400 pin connector is the 0 aperture, and the power supply module uses a 320 pin connector that's centered between the guideposts. Now you'll notice here that all these connectors look alike. They're all part of the Samtec C-Ray series. And that way it's been, there's really only one connector to go in and qualify, which is the reason that we chose that. We originally had blade style connectors that were reminiscent of what you would get for Vita 62 for the power supply. But after looking at it and looking at what it would take to go qualify that and the environmentals and everything, we switched back over to the C-Ray connector, which is what we're using now. And you see in the lower right-hand corner some actual photographs of one of the half apertures, the version with 6 coaxial contacts and 1 MT ferrule. So signal integrity, I mentioned before that we did an upgrade with Vita 90 to maximize signal integrity. And when we analyzed that connector, when we realized when we did Vita 90 that we wanted to go to higher speed bus speeds, we said, what's going to keep us from doing that? And we started looking at where we had the pin placement back in Vita 74 and said that we can improve that. So basically, Vita 74, as I said, was optimized for PC board routing and things like that. And it was good for Gen 2 because that's what was available at the time, and we were starting to go into Gen 3 and found out, yes, it works very well at Gen 3, but it didn't work very well at Gen 4. So Vita 90, we said we'd optimize it for signal integrity. And in a nutshell, the most important thing that we did is we put the longest contacts, which have the, on the right angle connector, which is what we're using on the module, we would put the longest contacts up in the S0, the utility plane section. These are all the signals that don't have to go very fast. And we put all of the high-speed data buses on the shortest contacts and organized the connector where we've got the first 5 or so rows in a 19 millimeter, let me back up, this 19 millimeter module uses nominally a 400 pin connector, and it's 8 rows by 50. And so we found that we put all the data high speed signals in the bottom 5 rows, and we put all the overhead signals and the low speed stuff in the upper 3 rows. And we found out that the signal integrity works great. And we can easily get Gen 4 and approaching Gen 5 speeds without any issues by organizing the connector in that fashion. So S0 is what we call our utility plane. And as you can see here, we have everything that's shown on this chart right now is what we call part of the utility plane, which and it's defined a little bit differently than it is in VPX, but we call this our common comms section for gigabit Ethernet, USB, serial, and a maintenance port. And this particular gigabit Ethernet in the utility plane is brought out as an MDI interface, as opposed to a KX interface, for instance. We have a full system management capability here with the geographical addressing and the IPMB A and B redundant system management pairs, as well as an I2C interface. And then we have all the standard NVMRO, reset clocks, GPIO, LVDS type signals, things like that. Now, one thing that's different on Vita 90 from that we hadn't really done before is we introduced a new concept called UEIO, which is unique external I/O. And these are 8 bits that are in every utility plane that you can use to go talk to peripheral devices that are not part of an I/O card. So for instance, you could go put an antenna switch or what have you over on the I/O transition board, which is the circuit board that would go to the outside world. You could talk to a small mini PCIe module over the I2C interface. If you needed to put that mini PCIe or that storage module out on the I/O transition board or on the backside of the backplane or what have you. So basically, or you could use it to talk to dumb modules. Like you have a module with a bunch of relays in it that don't require a full microprocessor-based interface and all the overhead associated with that. So these 8 pins is a tightly controlled rules-based configuration where you have some combination of I2C or SPI bus. And in the document, it defines exactly how those pins are used, so it's unambiguous, what the configuration of those pins are. So in the S1 section, that's the payload module where we have the control data and expansion planes, and that looks very similar to what was done in the VPX standard. Control plane is one ultra-thin pipe, and then we have an additional control plane in some of the profiles down in S2, which is our expansion region. And we have a data plane that we've got set up as 2x4 fat pipes, which may be concatenated if necessary. And then the expansion plane is set up as a by8 double fat pipe, but it may be bifurcated as necessary to give you the I/O that you need. S2 is our overlay segment, which can range anywhere from no pins. If we have a full aperture, we've got the bottom 240 pins in S1 and S0 and nothing left over for S2. But if you have a 320 pin connector, you can put a half aperture in there and have a set of overlay pins plus another control plane in that S2 segment. When we're sharing between MT and optical and RF and coaxial interfaces, we divide that into what we call S2A and S2B, where S2A is the copper and S2B is the optical and RF. Then if you have a 400 pin connector, then S2 is all 100% overlay section, and we've got that defined as far as what kinds of signals go in what places for one video, for 2 videos, things along that line. 90.1 is the module templates and profiles, and currently we have templates defined for the 240, 320, and 400 pin configurations. In the profiles we have defined for multiple types of video and different kinds of I/O, and I'm happy to talk about that to anybody. Power supply is 90.3. We've provisioned for 28 volts, 270, and 3-phase. We have balanced 12 volt heavy and 12 volt only. We made a decision to have the 5 volts and the 3.3 volts to retain those voltages because we're doing small form factor and doing that voltage conversion to be able to use some of the COTS modules in the marketplace, proved to be too difficult. But with the power conversion unit and the filter modules, we'll have a different style connector than the C-Ray. but it'll still fit into a 19 millimeter module. And the power supply units have been designed to be able to load share, so you get a bite-sized chunk of 65, 75, 80 watts or so per module that you can put together in parallel. And right now we're figuring a nominal of 3 power supply modules per system if they're needed. We've got Vita 90.4. This is an illustration talking about how we're going to be using. We're studying different materials for the module shell to be able to give you certain amounts of power availability, and then be able to use oscillating heat pipes to be able to move the heat to the proper faces on the module so it can be carried off. Pod mounted, one really nice thing about VNX is that it's a standard that will fit longitudinally within a 5-inch tube. So you can take a AIM-9X tube and put a backplane out there and have modules stacked in along the long axis, and it fits very well that way. So it fits into packages, into a 5-inch or a 6-inch package where other standards don't. This is a chart, and it's an eye chart, and I'll let you look at it offline. But basically everything to the right in solid blue is where VNX really lends itself. Everything in the middle is where short VPX is king. Everything over on the far left is 3U VPX, and everywhere in between they can kind of share. And the last slide is that VNX was designed from the inception to be able to fit into small CubeSats. So you can either fit these longitudinally or laterally, as shown here, in a typical 100 millimeter square CubeSat or the 2U, 3U, 5U, whatever CubeSats that are all multiples of that size. And there are manufacturers out there that are actually building Space VNX hardware today. That's it. Any questions?